Hey guys, if you're familiar with my videos on how to make your own programming language, then you'll know that in those tutorials, one of which I've kind of just, neglected a little bit, but I'll get to that. Um, you'll know that I've always sort of made a parser by hand, and I do think that's worthwhile. It's definitely worth creating a parser at least once, just so you understand how they work. But recently, just working on that code base has been kind of really exhausting, and I've just been trying to figure out what I want it to be and what I want the language to be. And at the end of the day, it's not really worth um like trying to support a full custom parser. There's no real reason to because there's already well-developed tools. One such tool is ANTLR, which we are going to actually implement in Kotlin in this video. You could use Java or any other of the JVM sort of languages. And you can use other languages too. It also is supported in things like C++ and C Sharp, etc. But anyway, for the sake of this video, what I'm going to do is I'm going to just quickly create a Gradle project. Just going to run Gradle Init. I'm going to choose to use Kotlin, but you can do whatever. If you're following directly along, I'm using Gradle 7. If your Gradle is too out of date, you might not get this sort of menu when you run the command, but I want an application. I want Kotlin. I don't care about that setting. I prefer to use Kotlin DSL for the build script, just because if I'm writing Kotlin, I may as well use the Kotlin script. That's sort of the way I think about it. I call this YT, obviously, is YouTube fastlang. I call it fast basically just because instead of spending all the time to make a custom parser and like a custom transpiler and everything, the goal of this, I guess this is sort of a new series, but this could also just be a standalone because one of the problems with ANTLR, especially with Gradle and Java, is there's so few resources to actually learn how to do it. I had to talk with ChatGPT for like hours trying to figure out what I was doing. And it's such a pain because ChatGPT is so out of date and like it really is so unintelligent. And then there's just so few resources. So that's why I'm making this, because I know that it's going to be really hard to just find one sort of solution to make it work. And I think I've found that. Of course, Gradle itself is kind of a nightmare, so you might have to argue with it a little bit. I had to spend hours doing that, but yeah. Anyway, again, if you've been following my channel, you'll know that I'm working on my own language called C, and it's such a horrible name. I really need to change that, but for now, I'm just going to stick with that. So that's why I'm going to call the project C, and the default package I'm going to call C. So now we actually have our project if I just display everything here. And let me just open this in Vim. And the first thing you want to do pretty much is just immediately go to your build.gradle. Now, personally, I don't want any of these comments in here, so I'm just going to quickly delete them in the least efficient way possible. I could probably do some kind of like replacement, but so this is basically what a generic Kotlin thing should look like. I'm going to update the Kotlin version from 1.5 to the latest 1.9. There's no real particular reason. It's just I kind of think that would be, in theory, it's better. It also means that this video, I suppose, people are going to be watching this hypothetically like into the next few years. So it would be better that I have more modern stuff. I am running Gradle 7 instead of 8 because for some reason my OS just doesn't have like an 8 built, so that could end up being a bit of an issue. But on the right side here, I basically just have a program I've already been working on to test this out. Okay, so first things first, let's just quickly run a Gradle build with the new version, and you'll see there's a few things here. Compile Java task, compile Kotlin. JVM target should be set to the same Java version, and this is also saying that. So what we can do to fix that, if we come down kind of anywhere, it doesn't really matter where you put this, but I'm just going to put down here. When we have Kotlin, we want to set the JVM tool chain to just something higher than like 8. I set it to 11 because that's what I have installed on my system, and that does seem to satisfy Gradle, so there's no more error with that. Okay. And I think now we're ready to basically get ANTLR up and running. One of the annoying things about Gradle is it's really not like set up out of the box to just create a jar file, which you would think is like one of the things it should really just do out of the box. So in fact, let's just see. You can just run assemble to sort of do everything. And the default place that it generates this is going to be, if I run java-jar, it's going to be an app build libs. And then in here, usually if you have no version, it's just called app.jar. But if you try and run that, you know, like you would anticipate, we're using Gradle so we can just build some sort of exe, right? In this case, it's going to be a .jar that we can just run with the Java command. And out of the box, it just doesn't work. And there's a few workarounds for that, but the one I found is just setting up some of our tasks, because it says no main manifest attribute, which means it doesn't know where the main function is. So before we even do ANTLR, it would probably be nice if we could just make this project work so that you can actually generate a jar with all your dependencies so that you can just ship that to people who want to use your thing. Now, there are other ways to do jars. They don't have to be fat jars. They're called fat because they include everything. They're going to be larger in size, but they'll have all your dependencies, and you can just immediately run them. I'm personally just going to do that because that satisfies my needs, but you may consider making a slim jar, which won't have all your dependencies. And I think you just have to, if you're doing that, you only need like the first line of this as far as I understand. But the important bit to make this work is we add this jar section so for the jar task. Although actually, what I like to do is I like to just make a tasks section at the bottom where all of the Gradle tasks, things like build or assemble, those will live here. And what we want to do is just modify the jar task, and we want to give it a manifest. We want to say manifest attributes, if I could type. And specifically, it says no main manifest attribute. And if you look that up, what that means is it's looking for a main class. And now, what you'll usually see is people do something like this, where they will say, it's like I don't know, project.main or whatever, because if you're working in Java, it'd be something like that. For Kotlin, you would just say c.appkt, but in my opinion, it's kind of weird to have the main class in two places. So the way I'm going to do this is I'm just going to reference the existing application main class property that's right up here. That way, if for some reason you ever want to change this, you can just come to this line and modify it, and you don't need to modify it in two places. Now, I think in principle that makes a slim jar, I think, but I want to make a fat jar, so let's get a list of the dependencies. I found this sort of solution on Stack Overflow. I think I'll leave a link in the description. I had to go through it, though. It's one of the just discussion things. So basically, we have a variable called dependencies, and we want to set that equal to configurations, and we want to, specifically, we want to take the configurations, we want to take the runtime class path to sort of get like all of the classes, I think. Gonna do a .get on that to get everything, and then we can map it and run zip tree on it so that we can zip all of those up, I think. I legitimately have no idea what this does, so I'm kind of just guessing, but essentially this is just going to take all of the dependencies. It's a long list. Okay. And then we want a duplicate strategy in principle, because there might be duplicates in here, and we want to set that to the pre-existing duplicate strategy exclude. So if there's duplicates, we exclude them. I misspelled dependencies in one of these. Probably this one? I actually can't, yes. There we go. So now with this set up, if we assemble again this time, and we try to run that, it actually runs the default program, just as is. And you can move that jar all over the place, and you should be able to just run it on pretty much any system with Java 11 installed, or higher. And that's the theory. One other thing you can do, if you're making a legitimate application, which I like to think that we are here, you can set the version. And I'm just going to set that to 0.0.0 until it's ever like in a good version. And then if we assemble this again, and I want to do an ls of app build libs, you'll see the app.jar is still there because we didn't do a Gradle clean. But because we assembled, we now have an app 0.0.0. And so every time you update a version, you can just come into this file, change the version number, and it will just generate a new jar for that version, and it will name it accordingly, which is very nice. So in principle, we actually can make a program legitimately now, instead of just living in this sort of development environment of Gradle. So now that we have just a simple hello world running from a jar, and I'm not really going to run it from a jar every time, it's just, I think if you're making a real application, you should probably have that set up. And I didn't know how, so I may as well include it into this. And luckily for us, we're trying to use ANTLR, which is just one of many different types of parsers. There's many you could choose, but ANTLR is a very reasonable one. And lucky for us, there's just a plugin for Gradle, so we could just come in here and say ANTLR. Now, this line caused me so many problems. You want to come into the dependencies, and you want to set your ANTLR version, because the default, if unspecified, is something like ANTLR2, and ANTLR2 will work with what we are doing. So the version I'm going to use, ANTLR4, is the latest, I believe, at least at time of filming, of course, 4.13.0. Expression ANTLR cannot be invoked. I think that might just be because we haven't actually built yet, so it doesn't recognize that it's here. So let's just try to run a Gradle build to download all the dependencies. And it did succeed, but there is a lot of extra stuff it says. And the big problem, I believe, is something along the lines of when you're compiling the tests for Kotlin, that requires the grammar source tests. Now, I might end up doing unit testing in this if this becomes a series. For me, I tend to just ignore it because I'm very lazy, but let me also quit Vim just so that perhaps that error should go away. But I think to fix this next problem, and I'm doing this on purpose, right? I could have just had you copy everything, but I want to show you what happens if you do it step by step, because it can be very confusing. So I think the next thing one thing we will want to do is we'll want to say generate grammar source, and we'll want to give an argument to ANTLR, and this is the task that ANTLR is going to run. We want to take the arguments, and we want to append something to it. Now, you can't just do a plus equals because reasons I don't know, but this is how you want to write that. We want to give the argument dash visitor. And what that will do is when the whole thing of like, what is ANTLR, right? I haven't even talked about that. ANTLR is a parser generator. So you can just have a single text file containing the grammar that you want to parse. This can be a programming language or mathematical sort of syntax. It could be regular expressions. It could be trying to parse like a phone number or just anything. You could even theoretically, you could parse an entire like spoken language if you could write down the grammar. Although I don't know if you could, because that might be like context dependent, or there's certain rules. There's a whole like theory about grammar, but you don't really have to understand all of that to do this, which is the nice thing. But essentially, ANTLR will generate a parser, and we can then utilize that parser, and we'll be able to, what the parser does, it will take the sort of like your input string, maybe that comes from a file or something, it could just be an actual string in Kotlin, and then it will generate a tree structure, an abstract syntax tree, that represents your grammar, essentially. And giving the argument of dash visitor will have it produce a visitor sort of interface for you so that you can implement that yourself to create a visitor. And what a visitor is, it is essentially just a thing that will go through your nodes, your tree, node by node, and do something to it. And that's how you could implement an interpreter or a transpiler or a compiler. Or maybe you just want to like do something else with it, that gives you options. So you're going to want this argument almost certainly. Now, we do have to still fix this where it says compile test Kotlin and compile Kotlin. So I don't think it actually gave one for compile Kotlin, but in principle, it should also need it. We could just say in the task section for the compile Kotlin task that it depends on the generate grammar source task. And if you're going to be unit testing and you're not just going to like erase all of the stuff that Gradle gives you, you can also say compile test Kotlin. And that also depends on, and in this case it says generate test grammar source. So now if we build this, you'll see that all of those problems go away. And in fact, we could probably just run this. Although it might complain. Okay, so it didn't complain. Nice. Now, whoa. Now, you'll have to, there's a very specific sort of structure that ANTLR expects when you're doing things like this, but if you just stick to it, it's like not too big of an issue. We can go into our sources, and you'll see normally there's a main and a test. I guess I can even show you specifically app.source using the lovely tree command, which is amazing. And you can see the structure that we have, right? We have a main. If you're using Java, this would be like Java, but we have Kotlin, and then C in our app.kotlin file, resources, and then the test section. What the application is expecting for this to work is inside of app source main. It expects a directory called ANTLR. And then from there, you can sort of give it whatever structure you want, but it will look for like .g or .g4 files. .g, obviously, perhaps not obviously, stands for grammar. 4 meaning we're using ANTLR4. So what you want to do, you want to name this file essentially whatever you want your grammar to be called, and it will name all of the classes accordingly. So, so let me create a c.g4 file. And so now that we've done that, once we actually build everything, we'll end up with like a C lexer, a C parser that we'll be able to use in our code. If you call this file something else, it will make it something else. But let's open up my very, very simple grammar on the right side. This is like pure just get this working proof of concept. The first line you'll want here is grammar followed by the actual name of the file. It will complain if this name is different from the name of the file, so you'll want those to be the same. Now, you'll often see people do something like a program for their first thing. It doesn't really matter, but what you need to know is that whatever you call the first sort of entry point, you'll have to actually run as a method. So it will give you your parser, which is like a C parser in this case, and you'll have to say something like this, if your grammar were set up like that. So in our case, we're just going to set it up sort of the way I've been doing it, because that's sort of just how I'm familiar. The root of my sort of language, I'm going to just say is a file statement, and I'm going to abbreviate stat. The syntax that people tend to use is they put a space and then a colon, followed by whatever else you want. Because notice that this starts with a lowercase, and that's important. This is what's called a non-terminal, I believe, meaning essentially it's not an endpoint, right? If you look on the right side here, a file statement is an expression, and an expression's an additive expression, etc. Meaning this is not an endpoint, whereas things that begin with capitals, and it only needs to start with a capital letter, but you'll very often see them be entirely capital. That's just sort of convention. Those things directly relate to like the single token, if that like makes sense. It's like one final thing, and there is no separating this out anymore. So for now, in the future, my file statement would be something like multiple statements followed by an end of file or something, right? And there are certain things that are built into this grammar. If you can get syntax highlighting and like an LSP for the grammar, then that'd be great. I can't find one for when I'm using Mason on Vim, so that's why it's just displaying a white blank text file. But what I recommend is there's a lot of examples of these sorts of grammars. So just sort of look at them and figure out what you want your grammar to actually look like. And that's honestly the hard part. Getting ANTLR to work is the easy part. It's figuring out your grammar that's the hard part. And if you're not familiar with regular expressions, you very much should brush up on that and learn how they work. Because this whole grammar is laid out using that sort of structure. So for now, my file statement, the root of all of my grammar is simply just an expression, because I just want this to work, right? And then an expression is going to be, for now, an additive expression. And then now we can get something a bit more interesting. An additive expression is, well, what do we know about additive expressions, right? If we have something like 5 plus 6 plus 7, well, what should that really be, right? We can't just make, well, I suppose we could make an additive expression like arbitrarily long, but what we tend to do is we tend to break things up. So actually, this is going to be 5 plus 6 as one expression plus 7 as a separate expression. And notice we split it up as 5 plus 6 instead of 6 plus 7 because you want to do this left to right. And now when it comes to addition, it doesn't really matter which order you do it in. I forget what the name of that property is, but addition does follow that property of math. But in principle, we would want to parse this left to right. Like you can imagine 5 plus 6 plus 7. You want to do 5 plus 6 first to get 11, and then 11 plus 7 to get 18. So in order to represent that, we want to do, we need an additive expression on the left, like we said. And then what we want is one of two things. Either a plus symbol or a minus symbol, because those are the two variants of an additive expression. And on the right side, we want a primary expression. You could also call the primary expression something like a term. There's a lot of different words that people will use for their grammars, and you can kind of call it whatever. I just like to sort of follow this structure. And then notice I didn't put a semicolon on line 7, on that line above, because we're not done defining this grammar. So when you have one line, you just put a colon, and then for the rest of them, you will just do a chain of ors to represent alternate definitions. And it could be either the top one, and if it can't be that, it could be the next. And so essentially, well, what happens if we're trying to build this expression, but we don't have one of these symbols? Well, then we should just return a number, essentially. And then we do the semicolon to terminate this. And so if you're unfamiliar with the way that grammars tend to be set up, then definitely read up on that and look at different examples. But once you understand that, this is a very simple way to just create a parser. Lastly, we just want to find our primary expression. Well, for now, primary expressions are just going to be numbers. And notice number is a terminal in this case, and now we can define our terminals. We want numbers, for this example, to simply be digits 0 to 9, one or more of them. And that's what the plus means. One thing I did interestingly, one thing I did before was I had a non-terminal be 0. I did something along the lines of a digit is defined to be 0 to 9, and an expression is like this. But actually, that's not the same thing, because an expression is then multiple digits, like as separate entities. Whereas when you write a terminal, it will take multiple of these symbols and create one token entity, you know? Now, lastly, I'd also like spaces to exist, but I'm not going to actually utilize those. So for now, for this sake, I'm going to have space representing a literal space and a tab symbol. You could also add like a /r/n, the other symbols if you want, but I'm going to actually use /n as a line end with semicolons for my programming language. So for now, for this example, I'm just going to ignore spaces and tabs. This by itself just defines the terminals, the specific, like, you could utilize spaces if you wanted to, but what you can also do is you can just do arrow skip. And what that means is when your lexer comes across any space anywhere, even if I didn't specify that there should be a space here, it can figure out that, okay, this is an example of this terminal, which is a space, and we're supposed to just skip those. And so that's essentially just our very simple grammar. Now we'll be able to actually go into our app. And, whoa, I don't like that layout. There we go. Now, for the sake of things, if we go in, I want to just quickly modify my app test, because like I said, I'm not going to be implementing unit tests, at least not yet. But one of the things I like to do initially is to delete the existing main class, because there's no reason to have that class. So what I'm going to do is I'm just going to come in here and delete that test. Let me just quickly run. And you see that doesn't break anything, which is lovely. So I'll just leave this app test class here. It doesn't really matter. Usually I just delete the whole test directory, and that doesn't break anything. But now we can go finally into our app.kt file. And you see what they do is they have a class that's called app, and it has just a simple field called greeting, which gives the hello world. But you can just get rid of the whole class, as long as you get rid of the reference to app here and the reference to app in the test that they pre-generate. And I'll name it 2 so that we can see it's different. And there we go. So now you might be asking, how do we actually use the ANTLR stuff, right? Because it seems like, you know, like what's even happening here. On the right side, you can kind of just ignore most of the top part. That's just going to be for the future so that we can actually print out our nodes. Okay, so what we want to do is we want to import, if you, actually, let me first look. Let me go into tree, app, build. The default build location for this stuff is in generated source. And you saw, oh, that's annoying. And you saw, you know, we did Gradle W run, which will build it. It will build everything. And you can see we already have stuff in here. We didn't even have to do anything. We just wrote a grammar file and then stuff was here. And again, it's crucial that your version is right, because in fact, I'll just show you what happens very quickly. You don't have to do this, but I just want to show the struggle I ran into, which I've only seen on one place, but basically now if we do Gradle W, let me just clean first to get rid of everything. And then if I try to run, you see there's an ANTLR panic, and you look up here, you see unexpected token grammar, rule grammar trapped, and all this annoying stuff. And it's like, I have no idea what that means. It means you're running a version of ANTLR that's wrong, and the way you're supposed to specify it is like this. And that actually solves the issue. And again, I can show you the generated source. So we have a base listener. You'll notice that some of these are .java, some of these are .interp, some are .token. Really, the useful ones for us are the .java ones. You see we have a base listener, and we have a base visitor. We have lexers, specifically one lexer here, C listener, C parser. Now, I will link the Java docs in the description. I highly recommend you read through them, because that's the only way I've really been able to figure out how any of this stuff works. But the basic idea is you have a lexer and a parser that you can just essentially use. But then after, you have 2 options. You have access to a listener interface, which is here, and you have access to a visitor interface. And both of them will essentially go through your tree and do stuff, but the listener is like a less powerful version of it, essentially. The visitor will be like, okay, we're going to these nodes, and you have to tell me which nodes to go through, and you have to do all this stuff manually. Whereas the listener is more like, you can kind of just be walked through the node, and you have to generate like a walker object to do that. It's very strange stuff, but it's not too big of an issue. The base versions are classes. So like I said, these are interfaces. The C visitor and the C listener are interfaces, but they provide a base implementation of those interfaces as a class, and that's what those are. And if we didn't specify the -visitor object in the build.gradle, we wouldn't have these visitor things. So if your goal is to interpret or transpile your language, it's very useful to have a visitor. You technically don't need it. You could just do it by hand. And in fact, the way I'm printing these nodes is by hand, for better or for worse. But there's a lot of useful utility in those that you can learn to use without having to reinvent everything. So now if I go back into app.kt, the first thing is, well, how do we actually, like parse anything? Well, first, let me actually go to the top in the slowest way possible. We want to actually import our C-lexer and our C-parser and anything else you want to use. Notice Vim's complaining, and that's probably just my setup because the files were generated like after the LSP started. It's really weird. But if you happen to be doing the exact same thing as me and see that, you can usually just fix that with a restart. Next, in order to access the ANTLR stuff, that's going to be an org.antler.v4.runtime. And then inside of here, there's tons of stuff. So rather than coming up to the top and importing things manually, I'm just going to import everything in there. And I'm going to spell that. ANTLR v4 runtime. You'll also probably want everything directly in tree. And there might be more things that we'll want later, but for now, that's essentially it. So now, let's just try and get this parser sort of working. You can parse from files, but just to showcase that we can use the parser, let's just make a string, and let's just call it input. And here we can just have our input. So let's do 58 plus 44 minus 3. In fact, let's make this a bit larger just so we can showcase that different size numbers work. Delete the hello world now. Now, in order to actually work on this, we need to create an input stream. And we need access to the built-in care streams. I don't know exactly where in the run. I'm guessing this is just in the runtime. This is going to be in part of the ANTLR runtime. And we can say care streams. And then we have some froms. And you see you have access to from path, reader, string, stream, file name, etc. So you have tons of options to make these streams that we are going to then pass into the lexer. In our case, we want to use from string, and we'll just pass in the string that we're using as input. Next, we can make our lexer. They provided the whole class for us. We didn't have to write it. So we could just do that, and it just requires some sort of input stream. Next, we want to actually generate our tokens. And we do that by making a common token stream that uses the lexer. Again, this is there's so much sort of just structural overhead, and that's really the big thing with using any sort of API library type thing. People have already made these decisions, and this is just how it is, and so you kind of just have to know how it works, which is really challenging. But anyway, it's not too bad with large language models helping out, but it's still kind of messy, especially when they're out of date. So now we have a list of tokens. That quickly, right? We didn't even write a single piece of code for our lexer. We just wrote the grammar. And then we can actually make an instance of our parser, which requires the tokens. Lastly, we can actually make our tree, which we can create by saying, we could take our parser, and you then have to reference the top level piece of grammar, like I've mentioned before. If you called it program, you would do .program. We, if you're following along, called it .file statement. So we can do that. And so now we actually have a tree. We could try to print this, but I don't think there's going to be that much to see here. But let's just try to run this and make sure we don't have any problems. And we have something there, right? I don't know what it is. So in order to showcase sort of what we have, unfortunately, we kind of just have to make a structure around this. We need either a visitor or a listener, or something that sort of does it by itself. And if you have been following my other tutorial series, you're going to recognize this tree string function, because it's basically the way I've always done things. And the reason is it produces something that looks exactly like the result of this tree command in Unix, which I think is a very nice way to represent a tree. It just looks very clean. And so you need those specific symbols. But we're just going to make a C printable tree class, and it's just going to take in our tree, which, of course, in Kotlin we don't have to worry so much about types, but the type of that tree that is produced is called a ParseTree. And it'd be nice to just have a like toString that just gives us the answer. And we're just going to call treeString using the built-in tree with a prefix of nothing. And I haven't really talked about exactly that yet, but we'll worry about that right now. So let's make a treeString function. It's going to take in some ParseTree node. It's going to take in some prefix. And what prefix means is, suppose we're trying to print this. Well, all of this stuff is the prefix. It's what comes before. And the reason for that, do I have any previous ones? This one. The reason is it's really hard to get these symbols in the right place. So the way I've found to do that is by using this prefix, essentially, so that those will be there when you want them, but not when you don't want them. It took me so long to sort of like refine that down, but now that I have it, it's just like I've just been copying it every time I've rewritten this. So our tree string is just going to return string. It could technically return like a string builder if you're trying to be really efficient, but I'm not trying to be that efficient. Now, there's a handful of different scenarios we could have. One such is we have a terminal node. There's basically three types of nodes, roughly speaking. There's terminal nodes, there are rule nodes, and there's error nodes. Now, I don't know exactly what error nodes are, but wow, it's like I really just don't want to enunciate today. I don't know precisely what error nodes are, but my guess is that if the compiler fails, it will still generate part of a tree. It's just some of the nodes will be error nodes, and you'll have to handle that. In my case, I'm just not going to really worry about that, at least not yet. So we really only care about terminal nodes and rule nodes. Terminal nodes are terminals, right? Like we defined num and spaces as terminals, and those will be in this tree as terminal nodes. Rule nodes, the other things that we had, things like expression or file statement or additive expression, are rules, and those are going to be represented as rule nodes. So we want to handle those separate cases. So let's create, before we even touch treeString, let's create a visit terminal thing. So that when we have a terminal node, we can just print it out. Because when you're at the end, right, you want to print it slightly differently than everything else. Although actually it's going to be more like that. And this is just going to return a string. So what we need, right? The question is, how do we get access to the symbols that we have in our grammar? Because what I've always done is I've essentially had nodes. Every piece of my grammar is represented with a class, and I print out the name of that class when I do this tree string, but I don't have that structure anymore, right? I'm using somebody else's. So but luckily, they do store everything for us that we need. So you'll notice C Parser and C Lexer have a thing called rule names. And I don't know the exact type, it says it's an array, but that essentially stores all of the names of the things that we care about. So I think, let me just simply, you don't have to necessarily do this. I just want to get that so it doesn't fail, and then you will want to do this at some point, but printable tree. We can just make a printable tree, which is a C printable tree, and we want to pass in our tree, and then we want to just print it, which we'll call the toString. And I'm doing that right now just so I can show you what is inside of cparser dot, what is it, rule names. And then in order to actually show that, you want not toString, but contents toString. or content to string. Yeah, content to string. If I run this now, there's just some warnings, but not a big deal. This is what we get. We get our file statement, our expression, our additive expression, primary expression. And those are all of our rules for the parser. And if we change that to our lexer, whoops, you could see we get some interesting stuff. We get num and we get spaces, but we also get these other things. My guess is these are plus and minus. It's just when you don't actually specify a literal symbol, which is in quotes, as a terminal, it will just generate one for you. So we'll just have to worry about that after, but it's not too big of a deal. So we know that these rules exist somewhere. The question is, how do you get access to the nodes, like which rule the node has? Well, it depends on if it's a terminal or if it is a rule node, but we'll be able to access both of those. I'm just going to leave that in here. Okay. So, in order to get the name of a terminal, we have to do, obviously, like I mentioned before, c.parser rule names. And it's an array that we can index. We need an index. Well, the index is going to be node. Actually, I was looking at the wrong one. The terminals need to come from the lexer. So we can say lexer.rulename node, and then what the node has is a symbol, and then using the symbol we can get its type, and then we have to subtract 1, I believe. Technically I haven't really tested all this. I basically just got it working, but if it's wrong we can always come back to it. But so this will give us the rule name, but that isn't enough, because that's not how I want to print it out. I don't want to print out like num, you know what I mean? I like to print tokens like this. So let's sort of just parse this using let to use what we have already. And so, well, if t underscore is in this thing, in the name, then I just want to do p because it's a punctuator. Otherwise, I want to just take the first character. And lastly, for the whole result, we could just give the ID followed by the quote symbols that I've shown. And you can just, I call this a name. I want to call it ID because it's actually a character, not like a string, so it shouldn't be a name. But that's it. Because if you print the node, if you print a terminal, it will just print the code that's in it. It will just print the like symbols. So, inside of tree string, we can worry about that again in a moment, so we can actually hook all this together. But there is another thing I want to do, which is to just clean up the tree structure. If we have a primary node, right, it'd be kind of wasteful to take another like vertical line like this. So what I like to do is I like to put the primary node on the same line as its terminal, rather than have two separate ones. So we could say visit primary, and you actually have access to like all sorts of things in here. If we have our parser, I think I even have expression context. I believe they do have a class for every single piece of grammar that you make, all the rules. Specifically here, we want a primary expression context. And that will say, these nodes are the primary expression nodes. Now we want to get access to the name, because there could be multiple primary expression nodes. And in order to get the name, this time we use cParser, and we take the rule names. And in order to get the name or the index, right, we need an index to go into this array. If you have a rule node, and this is a rule node, then what we need to do is node.rule context .rule index, and that will give us what we want. So that will give us the name of whatever this thing is. Then we want to get the child string, right? Because this is some node that contains some terminal. So in order to get the terminal, we can then do visit terminal. Another thing that these nodes have is the ability to get their children, and we can just get child 0. And we want to cast that to a terminal node so that all this works. I don't think that cast will ever fail, but hypothetically it could. Now you'll probably want to go in the description and copy this Specifically, these symbols, because these symbols, if you'll notice, is not the same as like just a couple of dashes. They're very specific, like Unicode symbols or something, and it just makes it look a bit nicer. So we now we can actually sort of build this, and the whole point of building this printable tree class is so that we can actually just print out our tree and see that it's working. And because it will be nice for debugging in the future. It really helps when you're designing your grammar to see how this will work. So, if the node that we have here, which is just a parse tree, if that thing is an instance of cparser.primary expression context, and specifically it is some primary expression whose child count is 1, because that's sort of all we're printing out here, right, is if it's a primary node with a single child, then we can return visit primary. If the node is a terminal node otherwise, well, we know how to do that. We could just visit the terminal. If the node is something that is not a rule node, which probably means it's an error node at this point, for now, I'm just going to return nothing. In the future, I might change that up, but my idea is just I'm not going to worry about it. So now, Kotlin actually knows that node is a rule node here. So let's get its name. cparser.rulenames at node.ruleContext.ruleIndex. And now I am going to use a string builder here. In principle, it's better than just appending strings to each other, but I really have no idea. I don't really care. I don't think this sort of like printable tree is really just for debugging, so I don't think efficiency is really the big problem anyway, but just whatever, you know. Now, what we want to loop through are all of the children. So the way we could do that is we can say, if I is in the range from 0 up to node.childCount. Ranges in Kotlin are inclusive, so we have to subtract 1. I don't think you need parentheses around that, because I think the range operator has lower priority. But to me, adding the parentheses just makes it a bit more readable. Because it's not necessarily obvious if you're doing 0 to like 1 minus 1 that this minus happens before this, because we don't have the spaces, because it just looks nicer without the spaces. So anyway, well, we want to know if we're at the end of this tree structure so that we can change the symbol we're using. When we're at the end, when our I is the child count minus 1. And then, again, you'll want to go to the description, copy these symbols. We want the symbol, if we're at the end, to be this sort of angle symbol that we can see up here. Otherwise, it needs to be this symbol, that continue symbol. And I believe these dash lines are the same ones that we use down below. So that will give us our symbol. And then, of course, we need to visit our children as well recursively. So we could say getChild at I is the current child. And then we need to deduce this symbol for this child. If we're at the end, there should be nothing. Otherwise, it needs to be this vertical bar. I guess I could just yeet that over. And now that we have the symbol for the child, we can actually generate the child's string. And we'll do that by recursively calling treeString. This time we're passing in the child, which itself is a ParseTree. We want to then place the prefix here, followed by the child symbol, followed by, I think, 1, 2, 3. I believe it's 3 spaces, it might be 4. But now that we have all of that information, we can append to our builder a new line, followed by our prefix, followed by our symbol, a space, and the child string. And it will then do this every single time that we loop through the children, and it will just keep adding on each of the children. Now, did I even mention that the string builder is initialized with the name? It's okay, I guess. Lastly, we want to do builder to string. In Kotlin, we can just do this, and it will call the toString for us. And then make sure down here that you're actually creating an instance of the printable tree, and then you can print the printable tree, which will call its toString. And now if we run this, you can see I actually have a tree structure that's pretty readable, right? We have a file statement. We have the nice angle without vertical lines going down because there don't need to be. The file statement is an expression, which is an additive expression, which in our case, we have 5838 plus 44 minus 3. And let's make sure we set up the order right. Well, it looks like we did because the 5838 plus 44 is itself a node. There is one sort of interesting thing. You'll also notice that we have an additive expression that is simply a primary expression. And you see, this is why I did this, because really, the additive expression could also sort of do that, but I think that would be a bit too cluttered. So I'm only just doing it for primary expressions so that it doesn't go down unnecessarily. But yeah, so we have this weird thing here, which is this additive expression is only a primary expression. But actually, that's not that weird because that's what we have our grammar as. In order to make this recursive, we say the additive expression is an additive expression plus or minus a primary expression, or an additive expression is a primary expression. That's exactly what we're seeing here. This is the case where the additive expression is only the primary expression. But because of how ANTLR works, the additive expression here is still included in this structure, which is fine. Like I said, this is for debugging. If you really want to get rid of that, that's up to you, because what ANTLR does is it generates a parser, and the parsing is done by it. All of the logic is done by you. So if you don't want that there, that's up to you to handle. But personally, I don't really care. But that's why it's there, because you might look at this and be like, why that's really weird, right? I mean, you might even be confused why the expression's still here, but it's the exact same reason. I kind of like it because it really just shows that your grammar is working. And so that's it, right? We just have this whole thing just got parsed immediately. And sure, we had to write some logic to print out the tree. That was a lot, but in terms of actually constructing that parser, it was, what, 8 lines? 8 lines plus a grammar file plus a bit of setup in the build.gradle. It's absolutely incredible. So just as a final sort of test, I want to assemble this, and I want to just test running this from the jar file, or proof of concept, right? Because in principle, we have this thing. I could go into app build libs, and I could just copy that jar out of there because it doesn't need a relative file structure or anything, right? I could just copy this app.jar. I could put it on GitHub. People can download it, and then they can say, let's just run the jar here, and there you go. It actually works. We just have an actual executable. We only had to fight Gradle a little bit to make it work. So I hope that my last few hours, I suppose last few days of just painful struggle against Gradle has helped you figure this out, because I think now that this exists, right? Now that I've figured out how to do it and I have a tutorial for people online, I think it's going to be so much easier. And if I ever forget, I can always come back to this video too, which is lovely. But it was such a pain to figure all this stuff out for the first time. And it's going to be a pain to figure out how to make a true interpreter or transpiler using this. But that's what the documentation's for. And it doesn't hurt to talk to AI a little bit. Although it's not really AI, it's just a machine learning algorithm. But anyway, I really hope that this was useful for you guys, because if a video like this existed 3 days ago, when I was trying to do this, it definitely would be useful to me. So I hope you guys enjoyed, and I'm excited to hear about what you guys do with this, Make something interesting. It doesn't even have to be a programming language, Like I mentioned before, you could parse pretty much anything like this. And maybe if you're parsing something like a phone number or a zip code, you don't necessarily need something this powerful, but it's a tool that is at your disposal, and you have the discretion whether or not to use it. And you could make a JSON parser. You could make a custom version. You could make something that's like JSON, but for whatever purposes you want, the sky is the limit. Whatever grammar you can define, this thing can parse. And it's it doesn't matter, right? It doesn't matter how complex your grammar is. This code is the same. All of this will work identically. You'll obviously just have to change how you print it based on what your structure looks like. But it's all up to you. So I hope this gets you excited to build whatever it is you're trying to build. And I hope that you don't run into errors with Gradle version stuff. Like I mentioned, I'm using Gradle 7 if that helps. But in principle, if you have Gradle 7, you should be able to type everything that I have, and you should be able to get every single dependency exactly like I do, and it should, fingers crossed, work. So one other thing you might consider is if you're having trouble with the jar specifically, it could just be your local Java version. Like I said, I'm running Java 11 on here, which is why I set my Java in the build.gradle to 11, but you just want to make sure that everything's working. And you don't even necessarily need to make a jar, obviously. It's just, in principle, if you're making a compiler or something, you'll want a jar so that you can just distribute it as an actual program. But anyway, I've been rambling too much. I hope you guys enjoyed this episode. I think I'll see you in the next one. I think I'll make another one on this, and I'll show you how to utilize this to actually, I suppose, just make like a real language. Let me know if you guys are interested in something like that. Either way, I'm definitely going to be spending my time working on it, so I guess I may as well make videos. See you then.